Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously we finished texture importing functionality which allows us to create different types of textures that are supported by modern graphics APIs. Today we are going to try and send texture data to GPU for use during rendering. So we spent the last couple of episodes on importing and organizing textures that can be used in our graphics engine for rendering textured models. As you can see, it offers quite a set of options for configuring what kind of texture we'd like to create and what BC encoding to use if you'd like to create a compressed texture. Now that we can import both geometry assets as well as textures, it's time to upload the textures to the GPU for rendering. Similar to how we upload meshes to the GPU, we first need to save the created texture to a file and read it in our C++ application. The asset interface has a pack for engine method that we see here implemented for geometry assets, and we can do the same for textures. Then we can add a temporary block that will save the texture data to a file for testing. In texture.cs, we already added the method, but now we have to write the code that actually puts the complete texture in a binary buffer. This is fairly straightforward once we define in what order we are going to put the information in the buffer. We start with a little header that contains width, height, and array size or depth of the texture. It will contain additional information like flags, number of MIP levels, and last but not least, the texture format. Next, we write each image in the texture to an array. For each image, we include its dimensions, row pitch, which is the number of bytes in one row of the image, and the slice pitch, which is the image's total size in bytes. In general, this is just a number of bytes that make up the pixels of the image, but it might diverge due to some alignment requirements. Finally, we write the actual pixels of the image. This is repeated for all images in the texture, such as MIP levels or each array element or depth slice in case of texture arrays and 3D textures. All we have to do now is create a binary writer and simply write our data in the order that we just defined. So first are the texture dimensions and other information. Then we loop through the 3D array of images and write each image to the buffer. Please watch these videos for more info about how this 3D array is constructed. Next, we flush the buffer and copy its contents into a separate array. This byte array is returned at the end of the method. Since you would like to also save this data to a file for testing, I'll copy this block of code from our geometry class and use it to save a single file that's called texture.image. Again, similar to geometry, we call pack for engine whenever a texture is loaded, and that will save the file. Let's go ahead and test it. Here we have a texture array and a 3D texture. We can open either one and we can see a new file appearing here with a size of 4 MB, which is the same as the data size we see here in the texture editor. Let me fix this error message while we are here. Okay, for the next bit, we are going to implement creating a resource from our texture data. Here in the test project, we have a function that reads a file and sends its content to the engine by calling the createResource function. In this case, it creates a resource from a mesh asset. We can copy and paste this code and reuse it for loading a texture. Obviously, we could call the same function and only pass the asset type that we want to be created, but this is test code and it's allowed to be messy and stupid. Looking at createResource function, we see that it can create materials and geometry resources, but we still have to extend it for textures. We can add it easily by repeating the same thing we are doing for creating a material. So I can copy this code and replace material with texture. Of course, this part should describe the format of the binary data that the function is expecting. These functions then call the graphics add texture and remove texture, which we are going to write in a bit. But first we can use these functions in the switch statement for creating and removing resources. We can add the high-level renderer functions next. I'll put these next to the submesh functions. We do have to be careful to use the right parameter types here. The implementation simply calls the low-level renderer functions, which we also have to add in a minute. To do so, first we have to add new function pointers to the graphics interface for adding and removing a texture. To this interface, we can then attach the low-level renderer functions, which will do the actual work. It seems that we already have declared these functions in the texture namespace of the 3D12 renderer. However, their implementation is still missing and needs to be done. As we can see in the CPP file, the function for getting a list of descriptor indices is already implemented, but not the add and remove functions. I'll copy this comment here again so we don't have to look up the format of our data every time. In the add function, we call createResource from texture data, which we are going to write a bit later. This function will upload the texture to GPU memory and return an instance of the 3D12 texture, which contains all information we need in order to use a texture for rendering. After the texture was created, we lock the container of textures and add it to the collection. I'll also add another collection that holds the descriptor index of each texture. This makes the array more compact since we only need the descriptor indices for rendering. Finally, the ID of the new texture is returned. In order to remove a texture, again we lock the containers and remove the texture and its descriptor index. Removing the texture will call its destructor, which will also remove it from the GPU memory. Here we add the free list of descriptor indices. We are going to write the function which uploads the texture data to GPU next. Although this is still not as complex as nuclear physics, it is more complicated than uploading meshes, so I recommend to take your time and try to really understand how a texture is presented to the GPU. First, we read the texture information from the buffer with the aid of our good old friend, the blob stream reader. We need to determine if the texture is a 3D texture. In that case, the value provided in the array size is actually the depth of the texture. For 3D textures, the depth value is divided by 2 for each MIP level, in the same way its width and height are divided by 2. We have to compute the depth per MIP level, since this information is not included in our data. To do so, first I create a static array of unsigned integers and fill it with ones. This is because all textures, regardless of their dimensionality, have at least one depth slice. If a texture is 3D, we swap the array and depth values. Remember that 3D textures can't have an array size other than 1. In other words, there is no such thing as a 3D texture array. To calculate each MIP level's depth, we loop through each level and divide the depth value by 2 for as long as it's larger than 1. Now we have all information about the texture ready. We only have to reformat it for the 3D12 API to understand. In order to do so, we have to fill in an array of the 3D12 sub-resource data. Then for each MIP level within each array element in the texture, we get the row pitch and slice pitch. We need this to fill in sub-resource data. As we see here, it needs a pointer to image pixels and the row and slice pitches. The pointer is the current position of our blob stream reader, and we can fill in the pitches as we read them from our buffer. Then we skip to the next image in the buffer. We don't have to put any information about each depth slice if a texture is 3D. The API will figure out how many bytes it has to read in order to get all slices. Next, we need to fill in a description of the resource that's going to be created. This is a D3D12 resource desk structure, which we can fully initialize. We used this description together with the number of sub-resources to calculate how much GPU memory is needed for this particular texture. Note that the number of sub-resources is simply the array size times the number of MIP levels. So for 3D textures where each MIP level consists of multiple images, we still count each MIP level as one sub-resource. We are going to ask our device what the footprint will be of a resource with this description and the number of sub-resources. We can use an array of placed sub-resource footprint structures. This will be filled in by Direct3D as we'll see in a minute. Here we can see that it contains a sub-resource footprint structure, which is just the format and dimensions of the sub-resource. It also has an offset that indicates where exactly in the buffer this sub-resource should be located. First, we have to allocate some memory to hold this data. We never need a lot of space for this array, so we can simply allocate it on the stack. The number of bytes to allocate is the size of placed sub-resource footprint times the number of sub-resources in the texture. In addition, we'll need two more arrays that will contain data about the number of rows in each sub-resource and how many bytes are needed for each row. Although we already know the width and height of our images, we must use the values in these arrays since they can be a bit different due to alignment constraints for texture resources. The total buffer size that is required to hold the texture is returned in this variable. To populate these arrays, we call getCopyableFootprints, giving it a pointer to the resource description, sub-resource count, and the three arrays for which we allocated space here. And the last parameter is a pointer to required size variable. Now we have every bit of data needed to upload a texture. We can use our upload context to transfer the texture to GPU memory. For this, we need to include the 3D12 upload header. Then we create an upload context with the required size. This will create a buffer that can be accessed by the CPU and can therefore be used to copy the texture data. We can get the address of this buffer to where we can copy our data. Each sub-resource is copied in a for loop where we get a reference to the layout and the sub-resource data. We also get the sub-resource height and depth. We define a copy destination that holds a pointer to pixel data, the row pitch and the slice pitch. We don't have to use this type, but it does contain exactly what we need for copying, so it makes it a bit easier for us. Then for each depth slice, we calculate the source and destination pointers where pixel data are read from and written to respectively. As I mentioned, the row size in bytes can be different from how many bytes are actually needed for all pixels on a row. This is because each row should be aligned to a 256 byte boundary. Because of this, we can't copy each slice in one memcopy operation. Instead, we have to copy the rows one by one. And that's why we are using a for loop here to copy each row. Again, please take your time to form a mental model of how textures are sent to GPU. It will help you a lot with solving issues when there are texture-related artifacts in your renderer. At this point, we copied all texture data to the upload buffer. The next step is to copy the upload buffer to another resource buffer that's only accessible by the GPU. We can create such a resource by calling createCommittedResource using a default heap and our resource description from earlier. This will create a buffer that's large enough to contain our texture. The resource pointer variable will contain the interface pointer to this buffer when it's created successfully. Using a GPU-only buffer is much faster, but we can't directly copy the data because it's not CPU accessible. Therefore, the only way to copy each sub-resource is by using a command list function. The function expects a copy location for the source and destination buffers. You can see here that it has a pointer to the resource that's going to be copied from or copied to, and a union that's either the placed footprint for the source or the sub-resource index for the destination. It will become more clear when I fill this in. Starting with the source copy location, the resource pointer is set to the upload buffer from which data is copied. The type should be placed footprint, which will tell the function how to interpret the union variables. Here we provide the layout of the sub-resource. For the destination, we set the GPU-only resource pointer. The type is the sub-resource index, which is just the index variable I. And finally, we can call the upload context command list function copy texture region to copy the sub-resource. Calling context and upload will execute the command list. At this point, the texture has been transferred to GPU memory and is ready for use. We can create an instance of the 3D12 texture using the GPU-only resource to initialize it. At the end, we return this instance. Looking at the constructor of the 3D12 texture, we see that it uses the initialization info to create a default shader resource view for the provided resource. Since it's a default shader resource view, it doesn't know when a texture is a 2D texture array or a texture cube. Therefore, if our texture is going to be used as a cube map, we need to explicitly tell the constructor to create a shader resource view of a cube map. And that's the last thing we need to do before calling it done. So here we have an SRV description which we need to fill in for a texture cube. If our texture contains a multiple of 6 images and it has also more than 6 images, that means that it's a texture cube array and we need to fill in the description accordingly. If it just has 6 images, then it's a regular texture cube. By setting the SRV desk pointer, this description will be used to create the SRV instead of creating a default SRV. So this was one of the longest functions that we have written so far, and of course you can feel free to split it into as many functions as you prefer. I don't have any objections against long functions as long as they do a single thing without any side effects. This function just takes in a blob of data and spits out an instance of the 3D12 texture, so I think it's just fine. And speaking of long things, this video is getting too long and I would like to continue in the next one, where we are going to test if we can upload a few different kinds of textures successfully. As always, thank you so much for joining me and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!